Hi everyone and welcome back. Our next speaker is a hacker, a neuroscientist, and an entrepreneur. She has a passion for democratizing biosensing and has been doing so with a kids wearable called Kiddo. This talk today is going to be all about open source, low cost biomedical sensing that you can do yourself. Please join me in welcoming to the Hackaday Supercon stage, Rintoul.
Hi everyone. Open source biomedical imaging. It's probably sounds a little bit like an oxymoron because obviously biomedical imaging seems to be expensive. It's in hospitals. Often we don't even get the tests that we really need to get because they're too expensive. We definitely don't get preventative tests. So I thought, wouldn't it be nice if we could do things preventatively, or we could get, if it was really easy to use, if it was everywhere, if it was accessible, biomedical imaging, you could get like preventative tests every year to say, oh, do you have a tumor? A year later, come back. You have a small one, you catch it when it's really small, and you do that instead. Right now, when people are really, really sick, you'll get some imaging done. And whatever's wrong with you will have progressed a long way. So it's sort of not ideal right now, and it could be much better. Speaking of dystopian worlds, the US doesn't seem to be the best with these massive expenses on healthcare, more than any other country. Yet we don't have like the outcomes, that we don't have the best health in the world to show for it. And the weird thing is, with all this money that's going into healthcare, you'd think that the technology there would be like rapidly innovating because it's so well funded, but that's not the case at all. In actual fact, the operating theater hasn't changed much in 30 years, which is sort of like really strange. Like something's up. So today I'm going to give a brief kind of overview of what's there right now in biomedical imaging, and then introduce you to this project that I've been working on based on a sort of R&D imaging technique called electrical impedance tomography. So, you know, biomedical imaging, we have an MRI scanner. They're big. We've got a CAT scanner. That uses X-rays that are rotated around a point. Ultrasound, which gives you those grainy images of babies when they're in the utero. And EEG, which I mentioned, but it's not an imaging technique, but it's still very useful anyway. So, sort of to understand and put it in perspective, like a CAT scan is a few $1 million, so is an MRI. It's certainly not something that you would like fiddle with in your garage at all, which is sort of sad, because one of the things that I think would be better is if people could actually experiment with medical imaging. It would probably move forward faster. Also, like CAT scans, they're ionizing radiation. That means if you get one done to you, you'll probably raise your risk of cancer. They actually don't do it to children at all because it will mean they will definitely get cancer later in life. They need lots of maintenance. Ultrasounds are much cheaper, $115K. Even cheaper again is EEG. For like a professional lab grade one, it's like $40K. There has been some open source action on the EEG front, which is fantastic with OpenBCI and the likes. So there are innovations going on that are sort of like coming back up towards moving towards medical imaging. And I wanted to point out these like 3 resolution columns. It's important to understand that there's like different dimensions to what an imager can do. So there's spatial resolution, which is what it sounds. It's like, how many millimeters resolution can you get? There's contrast resolution, which is like, what is the difference between materials? A CAT scan actually doesn't get very good contrast, but an MRI does. And time resolution. There's different things that go on in the body that have different time scales, like blood flow is really slow, but like electrical potentials like heartbeat or like signals in your brain are really fast. So applications, so these different imaging modalities are going to be good for different problems that occur with people. So you'll use whatever modality is best suited to the problem. And I put this on like a spatial and time resolution scale. Again, to come back to the radiation, CAT scans are the major source of radiation in humans in the United States. EEG is awesome, except don't read all this, but it has low, like 0 spatial resolution, which is a problem. Great time resolution. So that was an overview of imaging modalities as they are today. I'm going to talk about electrical impedance tomography. So I mentioned it's like this R&D technique. What you do is you send these very tiny AC currents through the body. And the body can be modeled as a circuit with resistive and capacitive components that are the cells. And as you send different AC frequencies through the cells, the current will actually take a different route. And you can measure that. So this picture up here on the left is what you call a phantom. We have electrodes around the edge, and we're actually sending through different signals. So we're sending AC signals through from one emitter to a receiver in a pattern around the edge. So we're sort of going around making many measurements. When you add them all up together, and I'll explain how you do this in a little bit, you can recreate an image of where the cucumber and the carrot was, which is sort of interesting. So far, this technique has been used for lung volume measurements, muscle and fat mass measurements. There's been some papers on gestural recognition with it, hemorrhage detection, bladder and stomach changes, and some new work on measuring the depth of anesthesia in patients. So what's nice about it is it's not invasive, it's really safe and non-ionizing, small, inexpensive, has much better source localization than EEG, say, and really good time resolution. Nobody knows about it, that's sad. And the spatial resolution is definitely not as good as an MRI, but perhaps there's still something useful that we can do with it. So just to remind people, when the MRI first came into being, this is actually the first MRI image just of a thorax, which is like a cross-section of your lungs. It's not that great, and we've improved it a whole lot. So this is actually my brain from like a year ago in an MRI scanner, and it's, as you can see, the resolution has improved a huge amount. And I just want to sort of put that there as a comparison to an early EIT scan. So that's an EIT scan of lungs as well. So we've got lungs there, and the question is, what's next? How can we improve this very simple technique? So I started fiddling with it. I made a GitHub project here, if you're interested in checking it out. It's all open source. The way that you can reconstruct an image is that as you send the different AC currents through at the different angles, they overlap, and they lose energy when an object is in their path of a different impedance. You add all that up, and each line that goes through is actually a line in this image on the right, which is called a sinogram. When you invert the sinogram using an inverse radon transform, you can recreate the image. So that's the basics. This algorithm is called back projection. There are other algorithms, but this one is actually the same algorithm that they use in CAT scan, exactly the same. So this is the PCB that I designed. It has 32 electrodes. It's based on a bunch of analog devices chips, like an ADU CM350 and some multiplexers. It's got Bluetooth, which serves to sort of isolate it as well, and sort of small power section. You're wondering, oh, you're sending current through the body, how safe is that actually? Well, it actually conforms to the IEC 60601-1 guidelines, which is less than 10 microamps. So if you compare that to products that are on the market, on late night TV, you see those ab things where people's abs spasmodically vibrate. Those are like tens of milliamps. This is less than 10 microamps, so very different order of magnitude. This is the open source software to do the image reconstruction, and this is what it does. Here I have a phantom and I have a cup, and I'm rotating the cup 1, 2, 3, 4, 5, 6, 7, 8 slowly around, and I'm recreating this image only with current. So the only information that it's getting to recreate the image is by sending small currents through. Here is 2 cups. You can see it can exactly place them. Again, you're thinking, oh, it's cups in a tank. And I remind you that this is what the first MRI scan looked like. And MRI scans are really expensive. They're millions of dollars, and often we don't get them because they cost too much just to get a scan, let alone play with one. As I was sitting at the dinner table, I wrapped it around my chest. This is my lungs. So you can actually see your lungs through it. You can see other things as well. It's really good at difference imaging because obviously you have air in your lungs. If you do time series measurements, because it's measuring impedance, you get a different kind of data than ECG, which is pretty cool. So you can get your lungs expanding and contracting, and the overlaid data, the smaller bumps, that's the heart rate. Now, this heart rate signal isn't the same as the ECG. It's actually caused by the volumetric change of blood flow through the valves in your heart. So it's a material change. So it's measuring these dielectric material changes, which is sort of cool. So extending that idea of dielectric material changes, over here, I put some fruit in a phantom. Excuse me. And I ran different AC currents through at different frequencies, and I got a spectrum. As you can see, the apple and the sweet potato have different spectrums. Like you can do it repeatedly, they have different spectrums, which is kind of cool. What that means that you could do is over here with a classifier, you can you do the EIT algorithm, you spatially localize, and you have a spectrum at every pixel. So I can use the spectrum to differentiate the material at every location. So here I'm able to detect where the apple is in the tank. Why that's cool is if you move that to, say, tumors or bullets or something else in a conductive body that you want to measure, it would be really useful. Maybe pulmonary edema, which is water in the lungs, by the way. So that's neat. That's open EIT. But you might be asking, what's the best that people have done with it? How good can it get? Well, in 2016, a guy called Kirill Aristovich, he put an ECOG array on a rat. So he lifted off the skull and he popped this thing just gently on the surface of the dura, is what they call it. And he got a 200 micron spatial resolution with a 2 millisecond time resolution, which is really kind of awesome and better than EEG in a lot of ways. So I've sort of shown you what it can do, And I'm just going to pop this image back up about, what we need a biomedical imaging system to do for it to be useful. So this has got the time and spatial resolution. Let's just say that EIT doesn't have the spatial resolution of an MRI. That's okay. Maybe there's some things that don't need that kind of spatial resolution, like tuberculosis. Tuberculosis is a really big problem in the developing world, by the way. So, a third of the world has no access at all to medical imaging. That's 4 billion people. Maybe we could do something about giving them some access while improving it along the way. Because this is something that you can do very cheaply. So, these are the lungs again. And as you can see on the right, you can see the lungs expanding and contracting with air. And you can see one lung doesn't have the amplitude of the other lung. Like on that upper right graph right there, it's quite visible and obvious to see. That's water in the lungs. Great. That's great. You could do something with that. So there's this. It's 32 electrodes, compliant with IEC guidelines. It's got Bluetooth. If you want to join the mailing list, it's mindseyebiomedical.com. And there's the GitHub. So what I want to talk about next is how it could be further improved. So wouldn't it be great if it was really good? If it was as good as an MRI? Why stop? So there's other modalities that are pretty cool. So as you all know, the FBI rule, so we've got AC current, so we've got force, magnetic field, and current. AC current is like a vibration. So then you have force, perpendicular, a vibration, otherwise known as a sound. So if you have, say, a little piezo array perpendicular to the current, you can potentially pick up very, very tiny sound changes at the same time as you're picking up current changes on the other side. And that would give you more information about the body that you're sending the signal through, and hopefully help you solve this very difficult algorithm to actually reconstruct the image. Obviously, you can increase the number of electrodes. So I actually started with 8 just to see if it kind of worked, and it did. And then I just thought, I'll just go to 32. And yes, the spatial resolution did improve. So that's pretty cool. So you can always add more electrodes, but putting electrodes on is annoying. So what else can be done to make this better? Well, right now the algorithms make all these very inaccurate physics assumptions. For instance, I was talking about the electrical properties of the cell before. So if you model the cell as a circuit, it's not a bunch of resistors. It's got capacitive properties, and there's very small inductive properties as well. Currently, the algorithms just assume this resistor circuit. Oops. They also assume that current moves in 2 dimensions. It moves in 3. So this is sort of similar to a lot of circuit analysis in a way, and maybe some of the circuit analysis tools need to move toward looking at the body. So time resolution, that's something that would always be good to improve. There's no reason why that can't physically or engineeringly be improved. It just needs to be done. Then write functionality. So I've only been talking about reading and seeing inside the body so far. What about writing inside the body? So there was this really cool paper in 2017 by a guy called Neil Grossman, and he used beat frequencies, and so 2 currents, AC currents, that had slightly different frequencies that created a beat frequency envelope that he could steer. And what he showed was that when the amplitude of the beat frequency envelope was at a certain level, he could get the neurons in that area to oscillate at the same frequency. So he could stimulate the neurons in a really controlled and focused manner with current. This is completely non-invasive, and I think it's sort of amazing and awesome. So you could do more with that. So like he did that. There's been some other work on beamforming with current, which works, by the way. So solving Maxwell's equations in a more complete way would be another great next step. Right now, the static model is used, which doesn't actually get you the sort of time-varying components, and the quasi-static model might be a much more thorough choice. So those were some sort of different directions that it could possibly go in. As you can see, there's lots of options there. I'd like to thank the open source contributors. This is some of us, we went to the International BCI conference at Asilomar earlier this year. And just the other day, we actually had a poster at IEEE Brain, which was like this advanced symposium for neurotechnologies, just sort of showing what we had so far. So coming back to technology and change, surgery used to be really barbaric. It was actually the same profession as hairdressing. That's where the word barber comes from. And what a barber did, he had scissors and saws. Scissors were for the hair. Saws were for, like, if you got a tiny little infection, they just sawed your arm off. And so that's, like, seems pretty horrific now. And now we have keyhole surgery. And keyhole surgery is definitely much more refined than a saw, but it's still not perfect at all, and you still need a lot of recovery time. What would be even better is if we had non-invasive bioelectronic medicine. So read and write current, sound, use microwaves from outside the body, and do surgery that way. That would be much better. We can see, if we can see inside and we can stimulate, that seems like everything you need to do something pretty amazing for human health. So I just wanted to say, like, thanks to everybody. If you want to, there's actually a discussion list, it's not a mailing list. And if you want to join the discussion on like open source biomedical imaging, and you think this is interesting, that would be super awesome. Anyway, thank you, everybody.